So when we adjourned last time, we had set up this problem in which we had sort of solved our, not really solved, but kind of set up our system of equations for this free particle that is incident onto a well. So here's the well. Somewhere up here is the free particle. And we had obtained as our energy eigenfunctions for this a set of 3 equations with 6 coefficients plus one more unknown, which is the energy. So we had a e to the I k1x plus b e to the minus I k1x. We had c e to the I k2x plus d e to the minus I k2x. And we had f e to the I k1 again x plus g e to the minus I k1x. These are for each of the regimes, x less than minus a, x between minus and plus a, and x greater than a, where this well is basically symmetric about the y-axis. So this right here has a value of a, this is minus a, and this is minus v naught. And where, of course, K1 and K2 are coming from the energies. All right, so 7 unknowns. Therefore, what we would normally need to do here is get for ourselves 7 independent equations in order to solve for all of this. Now, there are 2 boundaries present here. There's basically one boundary located here. There's one boundary located here. At each of those boundaries, we have 2 equations. Psi sub e continuous and d psi sub e by dx continuous. So collectively, this is 4 of needed 7. These are unbound states. So, you know, what we would normally do if it was a bound state is we'd say, all right, let's make this go to 0. So bound. So there's 2. That gives me 6. And then normalization gets me 1 more. And that would be it. We'd be done. The problem is that this is not a bound state. So for the unbound state, we actually kind of run into the problem that these 2 things as such aren't working for us. Energy is continuous. And then this means we have what is expected to be a continuous spectrum. And essentially, there's no need to decay to 0 at infinity because it's not bound. And so that also actually kind of makes normalization tricky. So what does this mean? So absent the normalization condition, we know E is now continuous. I've said that before. Um, and so for these scattering states, you have a continuous spectrum of scattered um, signal, essentially. Now, what can we do? What we can do, treat energy as an initial condition. And this is instead of treating it as an unknown. So that means that we've essentially played a little trick that gets us down to now 6 unknowns. Now, how might we go about all of this? And what might we do to get rid of some more unknowns? Well, so this is sort of 1. 2. Let's consider a typical scattering experiment. Oh, that's such terrible writing. All right, so what does a typical scattering experiment look like? Well, usually you have your target somewhere over here, and you have some set of particle that you're shooting at the target. And once this particle interacts with the target, essentially it scatters off of it either by deflecting or possibly by breaking through to the other side. Okay. And usually this is fixed in place target. Usually this guy is what's moving. So one of these may happen. It could also ricochet. But in one dimension, it either is going to bounce off of or it's going to essentially bust through the target. Okay. So usually for this typical scattering experiment, there is one projectile particle. It's usually moving. And one fixed target. So and usually this fixed target is also a particle, but in principle, this could become our well. The potential energy well itself is actually, for what it's worth, the interaction between these two. So the interaction between the projectile and the target. Okay. So now we say, given that we're considering this experiment, kind of continuing this thought, um, where does the particle come from, right? Well, usually the particle comes from some particular source. And so what we could do is maybe make the source, place source at, let's say, x equals minus infinity. So basically this is X source approaching minus infinity. In other words, the source is somewhere over here and it just kind of comes in from the left. If that's true, then this term, a e to the I k1x, has to represent the incoming particle. Okay. Now you get to the projectile, uh, the target of the projectile. In other words, you get to this first wall of the well. This right here is where our target basically is for this projectile. Granted, it's actually kind of up here, but we can treat it like it's here. And you have these two possibilities, these two possible interactions. There's reflection and there's transmission. Now, the reflection term, this is actually your b e to the minus k1x. And your transmission term becomes c e to the I k2x. Okay. Now, assuming that it is reflected, there's nothing further to happen. It just now leaves. It goes to minus infinity or heads towards minus infinity and never quite reaches it, approaches towards it, if you will. If it's transmitted, then you have a brand new scattering experiment, which is there is another target down here. And again, you can have this interaction in which it's either reflected or transmitted. Okay, this reflected one in turn, we expect to be some sort of a d. E to the minus I k2x. Now I put that one in quotes, and really this one deserves to be in quotes as well. And I'll mention why in a moment. This transmitted term, since it's moving to the right, would be my f e to the I k1x term. And there are no further targets. There's no reflected term, no reflection after this. Okay, the implication is that the G term for this typical experiment is actually 0. There's nothing for this thing to reflect on off this way, so we expect no reflection. Now, about these two that are in quotes. Why in quotes? Well, because they're not properly describing the transmission and the reflection in and of themselves. And the reason for that is this. I could transmit from here, hit here and reflect, hit here and re-reflect. And I don't have any new terms to use. And so, and likewise, I could then come back and reflect again off of this one. So I can have multiple reflections off of each target. So C e to the I k2x and d e to the negative I k2x together just represents particle or wave, while in, or properly speaking, over the well. Okay. So now what? Well, we can't really measure how many times does this particle reflect back and forth, or how many times does the wave, because again, we really should be thinking of this maybe from one projectile as mini projectiles. And so it's difficult once you get from one to many to measure how many times did this thing reflect back and forth within this well before it finally went out one way or went out the other. Okay. Um, the fact that we can't measure how many times this happens doesn't mean it didn't exist. That's sort of the follow-up discussion post class um, last time. But we can basically just say, well, the total amplitude of everything that is somehow between these two is this right here. Now, it would be nice to eliminate amplitudes C and D if possible. Why? Because if we can express C and D in terms of A and B and F, then we have, a slightly simpler system for ourselves. So taking stock at this point, we're down to 5 unknowns. A, B, C, D, F. And it would be nice if we could get rid of these two and make them, somehow functions of A, B, and F. Okay. Now, what C and what D really are doing, whether they are discussing transmission, reflection, that kind of thing, what they actually are doing is schematically the wave when it's right here, like anywhere in the well going this way, this is my C term. And all of what's in this well going this way would be my D term. And I guess while we're at it, this would be my A. This would be my B. And this right here would be my F. Which point is going to be very confusing for anybody who just simply looks at the slides without having taken note of the fact that this was a point that was added after the rest of this discussion. Okay. How might we try to get rid of these guys? Well, one way is that we can note that because this one right here is incident, that in some sense, all the other amplitudes must add up somehow to be this. So experimentally speaking, if I only send one particle and I'm able to measure that it's reflected, let's say, then I know immediately that this term has to be 0, and for that matter, that these two have to be 0. And again, if I send only one particle and I measure that a particle makes it over here, then I should also know immediately that there's no particle over here and that it has also exited the well. Similarly, if I send like 6 or 7 particles, or 6 or 7,000 or 6 or 7 billion, however many I want, as long as I can detect each particle either as reflected or transmitted, eventually I know that they all will have exited the well. And the number that were reflected plus the number that were transmitted should add up to the number that were incident. So number of incident particles must equal number of reflected plus number of transmitted. And these correspond to A, to B, and to F. I can control A experimentally because I maybe have control of how many particles I allow to be incident. So this is controllable. How many particles will I shoot at the target? Okay. So this brings us to what I would like to call the new normalization. Or maybe I should say the new normalization. And this is what we call R and T coefficients. And the way that this works is we're going to look at at the B over A and look at F over A. Okay, our normalization basically says that these two ratios somehow should add up to 1 in some form. Okay. Now, it is still true that we have a C and a D coefficient at some point, but since we are able to control A, we have made it so that we no longer have 5 unknowns. We now actually have 4 unknowns. And the good news about that is if you go back and keep track of what we had way back here, we have 4 equations that we get to have because of these 2 boundaries. And so having 4 unknowns means now we can start solving. So second upshot, since this is controllable, now have 4 unknowns. Essentially B, C, D, and F remain unknown. Everything else we've either set as an initial condition, eliminated, or we have control of it and get to essentially, control of it means you've set it as an initial condition. Okay. Um, Furthermore, taking stock of our equations at this point, that now looks like this. A, which we control, e to the I k1, which we kind of control, x plus b e to the minus I k1 x for x less than minus a, c e to the I k2x plus d e to the minus I k2x. This is inside the well again. And then on the other end of the well, we just have f e to the I k1x, since g has been eliminated. Now, let's apply the boundary conditions. Okay, so psi e of x continuous across x equals minus a. Okay, that basically means that this and this, these two top equations, have to equal each other at x equals minus a. So that means a e to the minus I k1 a plus b e to the plus I k1 a is equal to c e to the minus I k1 a plus d e to the plus I k1 a. Okay. Likewise, we have this must be continuous cross x equals a. All right, so now c e to the plus I k1 a and d e to the minus I, sorry, these are k2s, not k1s. These two are k1s, these should be k2s. And that is just equal to e, and this is now a k1 again. Okay, so those are your boundary conditions for function continuity. You also have this. And I'm just going to write these as this form to save a little space. These right here are kind of what we would just say phi e of x evaluated at x equals minus a. And this one right here we would call phi e of x evaluated at x is plus a for what it's worth. Okay, the derivatives. Well, you're taking a bunch of derivatives of exponents. Those are fairly simple, although because you're writing a lot of them down, there's plenty of space to, screw up algebra. The first one is going to look like a times I times basically k1x. So maybe we should just write this as minus ai k1a e to the minus and then I k1a plus, but when you take the derivative, you actually get a minus sign here. So if we're keeping track of signs, minus b I k1 a e to the plus I k1, so k1, not a ki, k1 a. And then on the other side, you end up with I times k2 times c times e I k2 a. Sorry, I messed up. See, this is what I'm talking about, having plenty of opportunities to mess some signs up. These two signs are both wrong. I'm taking the derivative. Okay, let me think about this. Taking the derivative of a positive term, so I should get a positive number. I'm inserting a negative. That makes this one negative. This one initially is negative. I take another derivative, it's positive. So in some sense, like these signs will be fine as long as you keep in mind that what I've essentially done is multiplied everything on both sides by -1. Okay. So here's I, K2, D, E. This is the -1. This is the plus sign. There. And this one right here, again, multiplying everything times -1. This one right here ends up being I K2 C e to the minus I K2A. No, I'm not actually multiplying anything by -1 here. Just doing this at the other boundary. You naturally end up getting this. Geez. Excuse me. All right, so that gets me my set of equations. And if you want, you can number these like equation 1. I actually originally did them in this order. So like in my notes, they're numbered this way, but it doesn't especially matter. I'm just numbering them to keep track of what I'm doing where. Okay. Now what we're gonna do is we really would prefer to just not have C and D. So in some sense, it's like we're not interested in C and D as much. Granted, you could calculate them and you could figure out like what is the amplitude of it, probability amplitude of its being in the well. But for an unbound state, which is not normalizable in the sense of being able to integrate from -infinity to infinity and get 1, the probability of any particle being in a finite well over time, as time increases, as time passes, goes to 0. So there is a sense in which these two numbers both have values, but also a sense in which we actually don't care what the value is. And so what we should do is use the two equations that I've numbered 3 and 4 to essentially solve for C and D in terms of F. Then substitute results into 1 and 2 to eliminate C and D. Now, if you do all of that, what you do, what you could do is also get ratios F over A and B over A. And if you do all of that, what you end up with is that the ratio of F over A is e to the minus 2I K1 little a over cosine 2k2 little a minus I k1 squared plus k2 squared over 2 k1 k2 sine 2 k2a. And for the other one, b over a, it actually turns out to be equal to I times f over a times, not equals, times k2 squared minus k1 squared over 2 k1 k2 sine 2 k2 a. What these actually represent is ratios of, so this is ratio of transmitted amplitude to basically incident amplitude. And this right here represents ratio of reflected amplitude to incident amplitude. Okay. In some sense, these are kind of analogous in optics to something like the little t and little r coefficients. And the squares of these is what we're really interested in. We'll define the t, big T, as...
Hi, is there someone wrong?
Huh? And this right here, when you square everything, remember when you take the modulo of this and square it, it's got a value of 1. So this ends up being 1 over 1 plus k1 squared minus k2 squared over 4 k1 k2 squared. Whoops. You know what? We'll just put a big square over this term. Sine squared of 2 k2a. Where, going back to here, we have made use of the fact that if you square these two guys, you'll have a cosine squared of this term and a sine squared of this term, but with different coefficients. And so we're essentially making use of cosine squared plus sine squared is 1. And then the other term, this part of the term, is like what's left over after that operation. Okay. And your R coefficient, this would be your B squared over your A squared. This ends up being basically T, the thing you found up here, times K2 squared minus K1 squared over 4 K1 squared, K2 squared, sine squared 2, K2A. Or if you'd prefer, it is 1 plus 4 K1 squared, K2 squared over K2 squared minus K1 squared, all squared. Sine squared 2K2A. Oh, sorry, this one is also in the denominator. These are what are called the transmission and reflection coefficients. They basically give you probability. So T, let's write this in a different color actually for commentary. T represents probability that particle is transmitted through well. R represents probability that the same particle is reflected from the well. Now, recall that K1 and K2 were actually just functions of energy. And in fact, actually both the total energy E and the potential energy V naught. So if we substitute back in to these equations and get kind of in terms of our original variables thing, transmission probability is 1 over 1 plus V naught squared over 4 E plus V naught sine squared 2A over H bar square root 2 times M times E plus V naught. R is equal to 1 over 1 plus 4 E plus V naught over V naught squared sine squared of 2A over H bar square root 2M E plus V naught. All right, and we're almost out of time, so a concluding note: if no particles are, we'll say, lost, so that would be absorbed, for example. Destroyed if we're using literal particles and they have like a spontaneous annihilation event, something like that. Then T plus R is 1. All right, according to my clock, it is now time to end the class, which is good because this is a logical transition point. Our next topic is scattering and resonance. And we'll just start at scattering and resonance. We'll stop there.
Okay.